What's up guys, Nafal here from Nemco. Today I want to show you how to plot model results on IMAT and the key stress strain parameters. We'll also be making general prediction on how the ground could react based on the assumed model input and based on the model mine sequence. Alright, without further ado, let's jump into it and make some cool animation and interpretations. We start off by providing some information about the model assumptions, and particularly here the far field stresses. The far field stresses can be represented by three components: sigma vertical, sigma horizontal 1, and sigma horizontal 2. The vertical component is the unit weight times the depth. Sigma horizontal 1 equals the K ratio times sigma vertical plus the locked-in stress. In this example, the middle zone of the model is at 500-meter depth. It is assumed that the major principal stress is horizontal with a K ratio of 2, while the minor principal stress is vertical. Here I would like to make a quick reminder of the different constitutive models. We have the commonly used Hooke-Brown nonlinear failure criterion expressed based on the UCS, MB, S, and A parameters. Another common used failure criterion is the linear Marco-Coulomb model that is expressed in terms of cohesion and friction angle. Same principle as Hooke-Brown. Below the criterion is the elastic zone and above is the plastic zone. Here I want to quickly address another more flexible and more realistic failure criterion called IMAS. IMAS is a strain softening model that initially uses Hooke-Brown criterion for the peak envelope but then switches to the post-peak and the ultimate strength envelope as material accumulates damage. In a stress strain graph, once past the peak, plastic strain is accumulated until we reach the critical plastic strain. Then from B to C, the deformation is governed by bulking of the rock mass. For the different materials used in this example, we have four units: host rock, ore, graphite, and faults. One important note is that the host rock and graphite are characterized by implicit formulation of joints in FLAC 3D. We model two distributions, vertical and horizontal joints. If we put the peak graphs of these units in one graph, we get this figure. You'll notice that the ore is the most competent unit, whereas the fault is the least competent unit. So let's jump into presenting the model geometries. In an isometric view, we can see that there is single to multiple parallel ore lenses, which sometimes complicate things. We have a ramp system and a level access to get to the ore and roughly 25-meter sublevel spacing. If we look at the cross-section view, we can see that the stopes are narrow to medium width lenses. We can also see that there are multiple mining fronts at once, which implies leaving some rock pillars, often called sill pillars, as well as some previously mined out zone on top that we made it bulky on purpose. So now let's present the mining sequence. We start off with developing, then we mine the first stopes on the far ends of the ore body, as well as the big mined out area on top. As time goes by, for every mining horizon we retreat towards the center axis, thus creating a diminishing pillar. So you can already guess that the last stopes in the mining horizon will be problematic. Also, another important point to mention is that we mine some uppers at the top of each mining horizon because we either don't have access or we lost it due to the mining sequence. Now let's get to the fun part. Here I'm showing the central cross section with deviatoric stress contours. As we are advancing in time, we start seeing that there is an increase of stresses and interaction between levels. As we are mining from bottom to top, we keep pushing the stresses, the high stresses into the rock pillars, including the sill pillars. These are indication of potential increased seismicity for seismically active mines and instability of the adjacent galleries. We can, for example, query stresses in particular location and plot them to evaluate the stress path and understand when issues may start arising. If we switch the view to a longitudinal view and step the model through, we can notice that the abutment stresses around the slopes increases. This is to be expected as the major principal stress is said to be sub-perpendicular to the strike of the ore body. One interesting thing to note is that the brows in the final stages of a mining horizon are particularly critical and extra attention should be paid when it comes to ground support. Uppers at the final stage are also particularly critical and extra attention and focus should be paid into designing these and properly recover these ore at risks. Here I just want to show you the risk at one particular level by looking at the evolution of volumetric strain with the mining sequence. Note that this model assumes subvertical joints, therefore most of the strain will be in the walls of the development rather than in the back, because in the back normal stresses on the joints help with the shear strength. And finally, if we look at the alternative model with subhorizontal joints and we look at the cross-section view of volumetric strain, you will notice that as the model is stepped through, an increase of strain and deformation occurs at the back of the development. And this increase is particularly important for intersections. So the design of ground support system needs to be checked properly in these intersections where the whole mine sequence is considered in order to de-risk these critical openings.
All right, well, that was a quick look on how to plot some key parameters and make some forward-looking predictions. Don't forget to start small when it comes to building large model and scale the complexity up gradually. Also, constantly calibrate and challenge your model. Feel free to contact us through our website or LinkedIn with your modeling questions.